Okay, so the other thing that we are going to explore is the idea of the specific heat ratio. So the specific heat ratio is defined by K. Now, we've already given you something K, which is thermal conductivity, which we talked about in heat transfer, and that's the only time we are going to be dealing with that K. And I kind of, when I talked about that K, I had a fancy script K that I worked with. This is the K value that we are going to really concentrate on for the rest of the semester. I'm not going to mention basically heat transfer or conduction, convection, radiation. That's the one thing that we're going to kind of put a pin in and give you the opportunity to work on that in your heat transfer class. But specific heat ratio K is defined as C sub P all over C sub V. Okay, so if this is what K is, and we said that C sub P is always greater than C sub V, then K values are always going to be greater than 1. Now you may forget, what is this ratio? How does this work? Just think about it alphabetically. The number higher in the alphabet, I should say, the number that comes first in the alphabet is on the numerator, and that comes later on in the alphabet is in the denominator. So that's how we remember this. Okay. Now we need to look at specific heats and understand how we use them, or how we get the information. And we can find that in our tables. So let's go look at our tables. I'm going to pull up the document camera, and the first thing I'm going to look at, now we've opened up another table here, table A19. I guess we actually did look at this table because it had thermal conductivity before. But it now has specific heat, C sub P. And now I'm in the SI table, and you can see that the specific heat changes. It needs a different amount of energy to change the temperature of something 1 degree. Okay, now look down here. Look at water. Water takes 4 times the amount of energy than some of these things like coal and granite and iron. It takes a lot of heat to change the temperature. Okay, so I didn't have air in here. Air is not in here, but air C sub P is about 1, and water C sub P is about 4. So it means it takes 4 times more energy to be added to water to change its temperature 1 degree, or removed 1 degree. And so this is why swimming pools are so popular in the summertime. The air temperature may be 100 degrees, but the water temperature may be 75. That's because we're still adding heat to that water and slowly raising its temperature. And then it's going to be slowly declining its temperature. It does not change as fast as the air. And we take advantage of that in swimming pools and also in power cycles. That's why we use water as our working fluid in our power plants to power around give us electricity. So that's important. Okay, table A19 is a nice table that we only has C sub P, doesn't have C sub V here. The next table I'll show you is A20. Now this is ideal gas specific heat. So we'll talk about ideal gases here in the next coming days, but here we're going to have different gases: air, nitrogen, oxygen, carbon dioxide, hydrogen, and it's going to tell you temperature in Kelvin, and it's going to give you the C sub P, and it's going to give you the C sub V. And because they want to be easy on us, they give us the ratio, even though we could do that ourselves. Now, here's a time when I say you can write something into your equation, your tables. We can put tabs in your tables. I don't want any real writing of equations, but let's go to the English table here, A20E. A20E gets me a lot, this A20E. A20E, notice what happens. Still the same thing, A20E, but now the temperatures are in Fahrenheit. You would think that since the A20 was in Kelvin, this one would be in Rankine, but it's not. It's in Fahrenheit. So make a note of that. It catches me every once in a while when I'm doing an equation. I forget about that Fahrenheit thing. So make a note that that's there. Okay, so that's table A20. Now we're going to go to our next table, and our last table is going to be A21. And this is the variation of C sub P bar with temperature for selected ideal gases. Again, we're talking about ideal gases, but this is showing us how the specific heat would change, and it's giving us an equation that we could use. Now we are not going to use this table a lot. This table is nice if we're writing a computer program and we want to figure out how the CSP changed with temperature. We could plug in this constant and get this equation, and then plug in our temperature, and we could easily find that. And it's a nice programmable thing if we were doing a computer program. But we're not going to be doing this a lot. But we will be using this footnote. And it says here, and I can't zoom in with my system I have here, but it says, for monatomic gases such as helium, neon, and argon, CSP bar is constant over a wide temperature range and is very nearly equal to 5 Hadz-R bar. Okay, I'm going to bring this up again, but this footnote, this single footnote, when we're dealing with helium, neon, and argon, and other monatomic gases is very, very important. So I want us to make sure it's there. I'm going to bring it up to us again. So those 3 tables are what I want us to talk about. Okay, so specific heat, and it's going to play a big role in how we solve some problems later on. Okay, it's a little bit of a shorter segment. We'll stop there, and then we'll move on to some property approximations.